stores thousands of student records used daily for registration, grading, and scholarships. But as data grows, searching becomes slower, especially during peak times like registration week. If our search strategy isn't efficient, staff and students face delays. That's why choosing the right search algorithm matters. This report has 4 objectives. First, we define the search need like exact ID matches, name prefix searches, and range queries for CGPA or semester. Second, we select candidate algorithms. Third, we compare them based on speed, memory use, and real-world trade-off for UNISZA. Finally, we recommend the most suitable algorithm to keep student record retrieval fast and reliable. Let's look at the findings.
For the justification section, our group selected 3 search algorithms to evaluate for optimizing UNISZA student record search system: linear search, binary search, and hashing. First, linear search is suitable for unsorted student record because it checks each record one by one until it requires information in found. It is simple to implement and does not require any pre-processing, making it suitable for small databases or databases that are frequently updated. Second, binary search was selected because it provides faster search performance than linear search. The algorithm repeatedly divides a sorted dataset into 2 halves, reducing the number of comparisons required. Therefore, it is suitable for searching student records that are already sorted by student ID or name. Third, hashing was chosen because it allows directed access to record using a unique key such as a student ID. By using a hash function, record can be retrieved almost instantly without searching through the entire database. This makes hashing highly efficient for larger database and frequent search operations.
Let's look at the system context. For system overview and impact, the UNISZA database stores records on many different students. The system assists employees in finding students using criteria like ID, name, faculty, CGPA, or semester. Because of this measure, in any search delay is a problem due to critical enrollment and grade calculation timelines. Looking at our database user, the system is accessed by registered staff for enrollment matters, faculty advisors for educational counseling, and office personnel for batch verification and report generation. Finally, we have 2 environment constraints. First, the time factor. Search requests are interactive and must process quickly under a second to keep workflow effective. Second, the memory factor. Memory usage must be carefully managed due to a limited capacity. Moving on to the system parameters, under search attribute and behaviors, our data field have specific traits, which is ID is a unique identifier return at most one result, making it ideal for exact match algorithm. Second, names consists of verify the string length required case insensitive or partial matching. Third is faculty and semester. Our categorical attributes with low cardinality means that they have a few distinct values that relative to the total records. And CGPA use a float data type spanning a continuous range from 0 to 4. For our dataset scale and purpose, the input value is modeled at n equal to 10,000 records, which is realistic scale for a mid-sized university like UNISZA. This dataset size can provide a practical baseline to evaluate the time and space complexity of our selected algorithm. Now, let's move to our data types and record structure. Under attribute specification, our fields are defined as follows. ID is a string or integer unique identifier. Name is a string up to 100 characters. Faculty is a string for the faculty name like FIK. CGPA is a float from 0.00 to 4.00. Semester is a string session identifier like 2025/2026. The setup directly drives our algorithm impact. The unique ID is our best choice for ultra-fast direct search like hashing or binary search. On the other hand, faculty and semester have a few categories, making them ideal for simple filter or split the data into smaller groups. Lastly, establish this performance baseline, set the context to test and compare algorithm speed under a realistic UNISZA workload. Thank you.
For my part of the project, I will explain the design selected and algorithm analysis for the student record search optimization system. The purpose of this analysis is to evaluate different searching algorithms that can be used to retrieve student records efficiently. The three algorithms selected are linear search, binary search, and hashing. This algorithm will be compared based on their search performance, time complexity, space complexity, and suitability for handling large student database. The goal is to determine which algorithm is the most effective for our student record management system. The first algorithm is linear search. Linear search works by checking each student record one by one until the required record is found. For example, if a user searches for a student ID, the system will compare the target ID with every record in sequence. The best case time complexity is O1, which occurs when the desired record is the first item in the database. The average and worst case complexity are ON, because the algorithm may need to examine all records before finding the target. The space complexity is O1, meaning it requires very little additional memory. The main advantage of linear search is that it is simple to implement and does not require the record to be sorted. However, it becomes slow and inefficient when the number of student records increases. The second algorithm is binary search. Binary search works only on sorted data. Instead of checking record one by one, it repeatedly divides the search space into two halves and eliminates the half that cannot contain the target value. For example, when searching for a student ID, the algorithm first checks the middle record. Based on the comparison result, it contains searching in either the left or the right half of the database. The best case time complexity is O1, while both the average and the worst case complexity are O log n. This makes binary search significantly faster than linear search. The space complexity is O1 when implemented iteratively. The main advantage is it is high search efficiency. However, student records must be sorted beforehand, which may require additional processing whenever records are added or updated. The third algorithm is hashing. Hashing uses a hash function to convert a student unique ID into a specific index in a hash table. This allows the system to access the student record directly instead of searching through multiple records. For example, when a student ID is entered, the hash function calculates its storage location and retrieves the corresponding records immediately. The best and average case time complexity are O1, making hashing the fastest among the three algorithms. However, in the worst case, collisions may occur, resulting in ON time complexity. The space complexity is ON because additional memory is needed to store the hash table. The major advantage of hashing is it is excellent search speed, especially for large database. The disadvantage is the higher memory requirement compared to linear search and binary search. To summarize, linear search is simple and memory efficient but becomes slow when the database grows larger. Binary search offers much faster search performance, but it requires the student record to be sorted before searching can take place. Hashing provides the fastest search performance because it allows direct access to record using a unique key such as student ID. Although it requires additional memory for the hash table, it is the most suitable solution for large-scale student record system. Therefore, for a university database containing thousands of student records, hashing is the most recommended algorithm because it provides the best balance between efficiency and scalability.
After analyzing three algorithms, linear search, binary search, and hashing, here's what we found. Linear search is simple and uses little memory, but with 10,000 records, it's too slow during busy periods like registration week. Binary search is much faster, but it requires the data to be sorted. Every time a student record is added or changed, the database must be resorted, which adds extra work. Hashing gives us the best average search time, constant speed, or big O1. Staff can retrieve a student record instantly using the student ID. It does use more memory, but the time saved during high-volume transactions is worth it. Therefore, we recommend hashing as the most suitable algorithm for UNISZA. The student ID is already a unique key, making it practical to implement. Binary search can still be useful for name lookups, but for the most time-critical searches, hashing is the best solution.